In this tutorial, we're just going to go over electrochemistry. So, what is electrochemistry? So, under electrochemistry, we basically get to study conversions between electrical energy to chemical energy and vice versa. Okay, so this is what we are interested in. And you're going to realize that under electrochemistry, basically, it is very useful in our day-to-day lives. This is something that we are working with. Even for you to be able to watch this video, electrochemistry is somehow involved. Okay, now let's first of all review a flashlight. So how basically do we get to produce light? How does it produce light? So of course it's right there being produced, but then remember that you're using a cell or a battery. Okay, there may be a battery or a cell in there. So now what you need to understand is the battery of a cell stores energy in terms of chemical energy. And then for light to be produced, there's supposed to be conversions from the chemical to electrical. So electrical is one that is going to cause the flashlight to be on. So there's that conversion from chemical to electrical energy. Not only that, you can think about a smartphone as well. For you to be able to perform a variety of functions on your cell phone, there's a conversion from chemical to electrical energy, because electrical energy is one that makes it possible for the phone to work, for the phone to turn on. But the battery that is charged stores energy in terms of chemical. That is the way it is stored. Think about a calculator as well. Calculator as well, there's need of conversion from chemical energy to electrical energy for it to be on. And also a vehicle, there's also a need of conversions from a chemical energy in a battery for it to basically go to electrical and then turn on the vehicle. So electrochemistry is a very practical topic that we're going to work with. And then, so in summary, we are saying electrochemistry studies the conversions, interconversions of energy between electrical and chemical energy. Okay, so we've talked about the real life applications, and we've therefore seen that it is very, very important for us to understand what basically gets to happen. Okay, so we have what we call electrochemical reactions under electrochemistry. So we can define an electrochemical reaction to be any reaction that involves the transfer of electrons. Okay, so it will involve transfer of electrons from one reactant to the other. So take an assumption to say, in a case where you have A reacting with B, and then to give you C and D. Okay, so where you have electrons being transferred from A to B, that is what we're calling an electrochemical reaction. So you notice that you talked about an electrochemical reaction to be a redox reaction, so which involves oxidation and what? Reduction. Okay, so what is reduction? We can define reduction to be the gain of electrons. Okay, so reduction is gain of electrons. And then we can also talk about oxidation to be what? Loss of electrons. So when you have two reactants, A and B, and then A is losing electrons to B, we can say A is undergoing oxidation, and the B that is gaining the electrons is undergoing what? Reduction. So these are called half reactions. So under stoichiometry, we had reviewed how we get to balance these redox reactions. So under the study of electrochemistry, like we've said, it involves this interconversions between chemical and electrical. We're going to have a cell that converts our energy from chemical to electrical, which is a common one. Okay, so this is a galvanic cell. We call that a galvanic cell. And then we also have another cell that will involve conversions from electrical to chemical energy as well. Okay, so these are the two cells that we're going to be talking about. All right. So now one thing that we need to understand is that, let me give you an example first of all. Okay, so now let's first of all review this concept where we have our reactant there. We have two reactants. And then this is what they're giving us here. So under the study of electrochemistry, it's very, very important that you're able to balance this chemical equation. Okay, so first of all, we need to understand. Let's try to identify the cell, the half cell or the half reaction. That is basically reduction and oxidation. So if you try to observe this one, you notice that there's a reduction in terms of there's an increase, sorry, so we call that oxidation. So an increase in the oxidation number is referred to as oxidation. And then when you try to look at the other one, we are moving from 4 to 3. Okay, so that is called reduction, right? We have moved from 4 to 3 there. And what does this mean? So this tells us to say that when you're moving from 4 to 3, it implies that we had gained a single electron, so which gives us positive 4 minus 1, giving us a 3 on the other side. And then when you look at the oxidation reaction as well, you notice that there's an increase from 2 to 4, which implies that there was loss in 2 electrons. So, but we're saying an electrochemical reaction will involve a complete transfer of electrons from one reactant to another. So all we are saying here, what is happening is electrons are being lost by one reactant to the other one. Okay, so this one is losing because it's being oxidized. So now if we are losing 2 electrons and then we are gaining 1 electron, it doesn't make sense, not so. So we want to make sure that the number of electrons being lost are equivalent to the number of electrons being what? Being gained. And that is what we call an electrochemical reaction. So basically what gets to happen is we need to know how we get to balance that. Let me just show it again. So how are we going to balance it? So in this case it's very, very simple. We first of all want to rewrite these as half reactions. And it's very, very easy in this case because all we have are the same reactants themselves. So I'll start with the first one. I'll write it the way it is on the reactants part, and then I'll write what is on the products part. Okay, that's what we have. So now we are saying it being a reduction, we are moving from a 4 to 3. It tells us to say that it was what? It was gain, right? So what are we going to do? We'll add an electron there, which will basically make sense because you do know that 4 plus a negative 1 is going to give you a positive 3. So this is a reduction reaction. And then on the other part, we're going to write the other half reaction, moving us from that part, getting us to what? Getting us to a 4, which is an oxidation because of an increase in oxidation number. This tells us to say we had lost 2 electrons, because if you had a positive 4 and a minus 2, it will get back to what you had. So this is what we have. Now we need to make sure that the number of electrons being lost is equivalent to the number of electrons being gained. So what are we supposed to do? The number of electrons, according to the reaction that we've written, the number of electrons that are being gained is single electron. The number of electrons being lost are 2. So we need to make sure they are balanced. The easiest way we can do is multiply the other reaction by 2, everything by 2, and then multiply the other one by the 1. So I'm just getting these coefficients from the electrons. Okay, so we have 2 there, we have 2, we have 2, and then we have 1. Everything else in the second half reaction will not change. So basically what you're going to have as a balanced chemical equation is something that is going to come out this way. So we'll have a 2 there, and then we'll have a 2 there. So you've balanced the redox reaction or the electrochemical reaction. Very, very important. If you're not very sure on how you get to go about that, make sure you check out the video that I worked on that involves a lot of practice questions on how you get to balance redox reactions. Okay, so now that we know what electrochemistry is all about, it's very, very important that we get to understand that we have what we call a galvanic cell, which we've said is very useful because it involves the conversions of chemical energy to what? To electrical energy, right? Okay. So now, it is going to base the concept on the aspect of the redox reaction, right? So we have an oxidation and reduction reaction in a redox reaction or in an electrochemical reaction. So the setup that we can have is where you have viscous. Okay. Let's say you have a solution now. You get to add your reactants, one being oxidized and the other one being what? Being reduced. So since we've said these reactants are going to involve the transfer of electrons from one to the other, so when you put them in a single solution, there's going to be a direct transmission or movement of electrons from one reactant to the other, and in such a case no use of work is going to be performed. So the setup of a galvanic cell comes out differently in a way that you're going to have one side and then the other side, where you would now put these two reactants in two different solutions, and then you get to connect them. So this is the way you're going to connect them using a wire. So we have a wire connecting our two reactions, right? That's what we have. And what basically is going to happen is these are called electrodes. They are solids. They are called electrodes, and that's a wire. So we now have a movement of the electrons from a side where there is oxidation. Of course, we've emphasized to say oxidation basically involves loss, right? So when we have oxidation on the left part, we expect that electrons are supposed to go to the other side, which is what? Where reduction is occurring. Okay, very important to note that. And then, what we need to expect is the oxidation part, we call this the anode. And then where reduction occurs, we call it what? The cathode. So this is a basic setup of a galvanic cell. Electrons will move from the anode to the cathode. Okay. But then you realize that if electrons are moving from one side to the other side, or what is on the oxidation part is going to be positive, the other side is going to be negative, and there will be no movement of electrons. Why? Because all the electrons are going to be used up on the left part. So what happens? How do we get to solve that problem? Because if you want continuous flow or sustainability of flow of current there, we would want to first of all have a balance the charges on both the anode and the cathode, and that's why we bring in the aspect of what we call a third bridge. Okay, so you have a third bridge, or you can have what we call a porous disc, which may be something connecting like this. Direct the containers, and it's a permeable membrane that separates it, and then you can put what we call an electrolyte in both the third bridge or the porous disc. So you can only work with one at a time. So that will be able to help you balance the charges in the two solutions and allowing continuous flow of electrons from the left to the right. And that's why this, if you get given a question in a case where they gets to put a bulb in between, they'll put a bulb in between. Okay, they'll put a bulb there, and then they'll explain. They may put a situation where they say the bulb was on for a short period of time and then it had gone off. Explain what had happened. So electrons basically will be depleted on one side. Okay, so electrons will stop flowing from the anode to the cathode because there is no balance of charges in the solutions. Yeah, so that's why if you bring in a third bridge, it will not go off and it will continuously be on. Okay, so this is the setup of a galvanic cell that we're talking about. So we've seen the flow of electrons, and that is our third bridge. So in the third bridge, as the name entails, we usually put a third there. Okay, an electrolyte. So that's what you have there. So this is a simple setup of a galvanic cell. So now, in our next lesson, we want to focus more on a galvanic cell and look at what we call the standard cell potential, calculations involving the Gibbs free energy, and many more things that are very helpful under the study of electrochemistry. We're going to go over a galvanic cell. So we do know that a galvanic cell is a cell that involves conversions from chemical energy to electrical energy. So in some textbooks, a galvanic cell may be referred to as a vortex cell. So whenever you say vortex cell, just know that you're talking about a galvanic cell. Okay, so to start with, we do know that in a galvanic cell, we need to understand that it's a spontaneous reaction. Of course, we said it's a redox reaction, so it's supposed to be a spontaneous redox reaction, which means that there's no need of us using any current. It is also going to happen on its own. Okay, so electrons will be able to move on their own, okay, from one reactant to the other in a redox reaction. So a spontaneous reaction, the standard cell potential is going to be positive, and the Gibbs free energy is going to be a negative. These are the things that we need to understand for a galvanic cell. So before we can move any further, we need to understand how we get to calculate what we call the standard cell potential. So now, as a student who has reviewed a galvanic cell, you need to be able to tell whether a galvanic cell may function or not by looking at the standard potential. standard cell potential. From the standard cell potential, you should be able to tell, because remember we've said it is supposed to be spontaneous. So now we always want to make sure that when we calculate our standard cell potential, it's supposed to be a positive, and if it's not positive, then it's not going to work out. Okay. So now these are what we call the reduction potentials. These ones that are attached to these half reactions, they're referred to as reduction potentials. So there's a table of reduction potentials. You don't have to master them. So these are the reduction potentials. So now, why are they called reduction potentials? They're called reduction potentials because if you've noticed, these reactions are all written in form of what? Reductions. So it's up to you now to be able to separate, and by looking at what you've been given, to see which one is going to be oxidized and which one is going to be reduced. As things stand now, what we want is to get a positive standard cell potential. So now, whenever you get to reverse a half reaction, the sign of the reduction potential changes. Okay, so that's one thing that is very important. Now, assume we reverse the second half reaction. So it's going to be positive 0.23 volts, and that would mean that this will now become our reactant, and our reactant will become our product. Okay, so this is what we are saying. Okay, and then we'll have our two electrons there. So this will imply this is now an oxidation reaction, and what you've noticed is I've changed the reduction potential, it has become positive. Okay, now is it feasible? Is it going to work in such a case? So we calculate the standard cell potential by basically adding the reduction potential and the oxidation potential if a term does exist. But I can say we had the reduction potential of an oxidation reaction and also for the reduction one. So I'll get my negative 0.76 and then I'll add the 0.23. So you're going to notice that this is still going to give us a negative value. Okay, so now try to perform a calculation there and see what you're going to get. So you'll be able to understand that this is not a feasible reaction, because minus 0.76 plus 0.23 is going to give you what? A minus 0.53. So this is not, it's not possible to have such a galvanic cell. So which tells us to say that we're supposed to do the opposite instead. What are we going to do? We're going to reverse the first one. So we'll reverse the zinc reaction so that we have the solid on the left, and then we have zinc 2 plus 2 electrons there. So what you have is now a positive 0.76. This is very important each time you are calculating the standard cell potential. Okay, so you just have to add what you have now. You have your 0.76 plus a minus 0.23. Okay, so in this case you'll notice that now your result is going to be what? Is going to be a positive one. Okay, 0.53. So now this galvanic cell in this kind of a setup is feasible, it can work. Okay, so that is how you calculate your standard cell potential when you're given half reaction. So it's up to you to know and to understand which one is going to be oxidized and which one is going to be reduced each time you're given two half reactions. Okay, now that we know how to go about that, it is also very important for us to understand that we can also call our standard cell potential, or our cell potential, to be our cell potential can also be called EMF, which is electromotive force. Okay, and that's why it's measured in volts. Okay, so this is basically just the force that is putting electrons from one side to the other side. That putting force that makes it possible for electrons to move in a galvanic cell. Remember we said this is the basic setup of a galvanic cell, where we have electrons moving from one end to the other. Okay, so now why we're calling it the standard cell potential is because standard cell potential is measured at what? Standard conditions at 1 atm. So take note, these are the standard conditions: 1 molar concentration and also 298 kelvins or 25 degrees Celsius. So these are just the conversions between Kelvin and degrees Celsius. Any of the two is okay. So these are the standard conditions that we need to take note of. Okay, so now that we know how to deal with a standard cell potential, we should be able now to convert a galvanic cell that is drawn, given in terms of the reactions, and be able to present it in what we call line notation, which is also called shorthand notation representation of a galvanic cell. Okay, so equally, if you look at the given reaction here, so it's also possible to have a positive reduction potential. As we can see, the reduction potential of the standard reduction potential of copper 2 plus is a positive. So now, what are we supposed to do for us to determine which one is going to be oxidized? So now, equally, we need to make sure that our standard cell potential after reversing a reaction is supposed to be positive. So if we reverse the one that is down, it is very obvious that everything will remain negative and it is not possible to have such a galvanic cell. So alternatively, what we can do is reverse the one that is on top, right? So that we get to have what? A positive cell potential, standard cell potential, that is. Okay, so now one thing that you also need to understand is, that I've not talked about, is it is also possible to have a case where one half reaction may have a single electron, and in such a case, you would need to balance up things. Now let's take an assumption to say, maybe if we had copper 1, for example. So if we had a copper 1, you've seen that there will be a single electron there, and we said in an electrochemical reaction, the number of electrons being lost is supposed to be equivalent to the number of electrons being gained by the other reactant. So in such a case, we would have multiplied the reaction on top by a 2, so that we balance the number of electrons. Every reactant and every product was going to be multiplied by 2. Okay, in a case, this is just the same way we used to work out with simultaneous equations. So now let's assume if we had the 3 there. As it stands, we would have to multiply the one on top by a 2, everything by 2, so that the electrons will become 6, and that would be 2, and then the other one multiplied by 3 would be something that is going to come out that way. So at the end of the day, you have an equivalent number of electrons. So whenever you do multiplications, what you need to understand is the standard cell potential remains, or the standard reduction potentials will remain the same. Okay, so that is just necessary when they want you to come up with a balanced chemical equation for the given half reactions. Okay, in a case where they just want you to calculate the standard cell potential, it is not necessary, because these ones don't change. They only change signs when you reverse the reaction. So as things stands now, our standard cell potential is going to be the addition of what we have. So 0.34 plus 0.76 will give us a standard cell potential, which is 1.1 volts. Okay, so this is our standard cell potential at 180 m, 1 molar concentration, and 25 degrees Celsius, so 298 Kelvin. Okay, so now how do we get now to convert this reaction into a line notation? So we've seen the actual way in which it's going to be presented. Okay, so now our balanced equation will involve us combining these two. So these electrons are basically on opposite sides, so we'll cancel them out, and then we'll drop our reactant. So we have copper 2 plus what? Plus zinc solid, and giving us what? This is giving us a zinc 2 plus, and then we also have copper solid. So I'm going to erase the top part to just help us see what we can do there. Okay, so one thing that you need to understand is we're always going to show our anode on the left hand side in our line notation. Okay, we're always going to show it on the left hand side. So in this case, we do know that basically the anode is basically the one where oxidation occurs in a galvanic cell. So which reaction is an oxidation reaction? It's the second one, right? This is why it was necessary for us to understand or be able to identify which one is going to be oxidized, because we need to show that on our line notation. So zinc solid, and we always show the electrodes on the leftmost and the rightmost. So knowing that on the left side we are having the anode, the electrodes basically, when you have this kind of a half cell in a setup where you have a galvanic cell like that, this is what we call the electrode. So electrode makes it possible for conversions of the current, it allows the electrons that are coming from one end to be able to interact with what? The solutions in which it's placed. So we always want to make sure that the electrode that we have is in solid what? State. So that is what we're going to be putting on the leftmost. So if you observe our oxidation reaction, the solid that we have is zinc. Okay. So now we use lines like this one to separate different states. Okay, that's what we need to know. So we'll separate the electrode from what is in our solution. In our solution there, ladies and gentlemen, we're going to be having what? Solid. We're going to be having aqueous states. And in this case, what we have in aqueous for our oxidation reaction, I'm sure you're able to see that what we have is what? It's zinc 2 plus. So I'll put zinc 2 plus. Okay. Now when you are done with one side, that is for the anode, the oxidation reaction, we'll put two lines. Instead of putting one, we'll put two. So these two lines now, on a shorthand notation, denote what we call now what we are calling a salt bridge. So very important for us to note that. So this is what we're calling a salt bridge. Okay. And then the other side, as you might guess, I said on the rightmost we need to have what? We need to have the electrode for the reduction of reaction. So it's copper solid at the end there. So in between, as you might guess, is supposed to be what? What is in the solution, which is copper 2 plus in aqueous states. Okay, very simple. So this is very simple for you to do it, and very easy for you to follow up. Okay. So now let's try to review a case where you may not have an electrode. Let's say you have two. So these are our reactions. Okay. Giving us hydrogen. So you notice that in this reaction there's no solids. How do you get to approach such a question? So now let me put another one for the sake of us being able to understand how we approach such a question even when they want us to perform other calculations. So we have 0 volts as our reduction potentials for these two reactions, shown respectively on the right part there. Okay. So now we need to first of all understand which one is going to be oxidized and which one is going to be reduced. Our major goal is, after reversing, we still want to have a positive value. So we do understand that reversing the 0 there, the top reaction will not change anything. But if we try to reverse the one that is on the bottom, our standard cell potential is going to be a negative. So it is fully dependent on the second one, right? It has got an effect. So we are not supposed, if we change this one, it will be a negative answer. If we leave it the way it is, it would require us to change the other one, which is more favorable, right? So we'll reverse the one on top, so that we have hydrogen gas giving us our hydrogen ions in the solution plus 2 electrons. So this is interesting because we don't have a solid. So what are we supposed to put on our electrode? Okay, so the standard cell potential can be calculated by you just adding the 2, which will just be 0.34. And then what else are we going to do now? We are more interested in how we get to come up with a line notation in such a case. So as I said, we'll start with the oxidation reaction on the left. Now notice that in what we have, we don't have a solid. So an electrode is very, very cardinal and very important in a galvanic cell. So therefore what we're going to use instead is what? We're going to use non-reactive metals like platinum and lead. So we'll use platinum in this case. So I'll put platinum as our electrode, and that is why I had to give this example, because it's very, very important to understand that you can use platinum as well. And then I said, after you've shown what is on your electrode in the oxidation reaction, what are you going to do again? You need to put something else as well. Now what do we have in this case? So I'm going to show these other things that are remaining with the hydrogen gas and the hydrogen ions. So if these guys were in the same state, let's assume even what is on the left was in aqueous, I would have just put hydrogen, aqueous, and then I would have separated them using a comma, and then I would have shown the hydrogen ion that way. That's what we do whenever they are in the same states. Now, it seems these guys are in different states, so I'll still use a line to separate them. So I'll start with the hydrogen gas, and then I'll still draw a line because they are of different states, and then I'll show the other guy there. So okay, so we have the hydrogen what? The hydrogen ion there. So let me show it. So we have the hydrogen ion in aqueous state. And then the other side, what do we expect to have? So I'll put the salt bridge there. Why the salt bridge? Because we are done. And then the other end, what do we expect to have? The other end, as usual, at the rightmost, we're going to show what? We're going to show what is on our electrode. In this case, it's copper solid, right? There is it to follow up, and this is just going to be copper 2 plus aqueous state. So you've shown everything. The only unique thing about this one is what we have is we have what? We have this kind of separation, and then we didn't have a solid reactant in our reaction. So it was the necessity of us looking at this was how do we get to approach it. Okay. So that in this short tutorial, we're just going to go over Gibbs free energy. Okay. So what is Gibbs free energy? Gibbs free energy is just the available energy of a substance that can be used in a chemical reaction. How much of the energy is available to perform work or useful in a chemical reaction? That is Gibbs free energy. So a Gibbs free energy in a given chemical reaction is going to be dependent on the number of electrons multiplied by the Faraday's constant and the standard cell potential. So now, what we need to understand is N in this case denotes the number of electrons being transferred. That is the number of electrons being lost in the anode reaction, in the other moving to the cathode, right? And then F denotes the Faraday's constant, which is 96,485, right? So we also need to understand that the units for the Faraday's constant are joule per volts mole. So those are the units for Faraday's constant. Then our standard cell potential, we have already reviewed how we go about it, how we calculate it. So sometimes it may be given, sometimes we should be able to do it given the reduction potentials of half reactions. Okay. So now that we know what to do and what to plug in, let's try to review the question that we have. Just before we go any further, we would also want to talk about the remember we said a case where our standard cell potential is positive, we say that denotes that our reaction is spontaneous. Now for the Gibbs free energy is the opposite. Whenever it's negative, we can clearly see that the reaction is what? Is spontaneous as well. When it's positive, it tells us to say it's non-spontaneous. So don't forget that it's a negative that is part of the formula there. Okay. Excuse me. Okay. So now what we have in this question. So we've been given the standard cell potential. Then we need to determine the number of electrons that are being lost in one reaction. So this is the anode reaction. We can rewrite it. I'm sure we're clearly able to see it before writing to say we are moving from 0 to 2, which implies that to say, since this is the anode reaction, so 2 electrons were what? 2 electrons were lost. Then the other side, if you check, again you have 2 and the 0. So that also entails to say 2 electrons were gained, right? So the number of electrons are already balanced in this case. So we'll just substitute. Where N, we are putting 2. Faraday's constant, 96,485. And then we'll put our standard cell potential there, which is already given as well. So that is 1.61, right? So using, if you try to review what you have here, perform the calculation. So negative 2 multiplied by 96,485 multiplied by 1.61. Okay, so I'm getting a minus 310,681.7. So now what are the units? What are the units that we expect to have? So remember, this is denoting the mole of electrons. Then this is denoting, we said the units for Faraday's constants are J, then volts mole, right? And then we're multiplying against the standard cell potential, where the units are volts. and then multiplying against some more, right? So at the end of the day, we'll remain with jaws. Okay. So now whenever you have a bigger value like that, you would want to divide by 1,000 to just make it look neat. So if you divide by 1,000, the answer that you're going to have is negative 310 or 31 kilojoules. So that is your answer. Second question says a galvanic cell with a maximum cell potential of that. Of course, that is our standard cell potential. In an experiment, 1.33 moles of electrons were passed through this cell at average. So you have the average what? Standard cell potential, or let me just say the cell potential. Then you're asked to find the maximum and the actual work done. So now this is where we get to understand to say our Gibbs free energy is basically equivalent to what? Is equivalent to work for any information. Whenever we're asking about the maximum work, just know that it's equivalent to what? It's equivalent to the Gibbs free energy. Okay. So now in this case where they want the maximum, we're going to get the maximum standard cell potential. Okay. So maximum work is going to be N, since we are saying these are the same. And then the number of the moles of electrons that we have is 1.33 according to the question. So notice that in this question we don't have the half reactions to help us determine the number of electrons. So we'll look at the moles given and put where there's N. Third is constant, 96,485. Okay, that is joules. And then multiply against the standard cell potential, which is a maximum 2.5, right? 2.5. So after performing your calculations there, what do you expect to have your answer? So 1.33 multiplied by 96,485 multiplied by 2.5. I'll divide by 1,000. So what I'm getting is 321 kilojoules. So that is the maximum work that was done. Okay, so it's supposed to be a negative. Okay, so negative that. And then find the actual. So the actual work done is dependent on the non-standard cell potential that was actually going around. That was actually moving the electrons. And that's what we're given there. So the only difference that we have here is we are going to basically multiply by that. Where we had the cell potential, we are going to put the 2.1 instead of the 2.5. So you can try that out and see the answer that you're going to have. And finally, the last question. The oxidation of hydrogen by oxygen is one of the most used reactions in fuel cell technology. The overall reaction, which is given below as the standard cell potential value of that, what is the standard cell potential for this fuel cell? So this is the case where they've given you now the standard Gibbs free energy, and then they want you to find the standard cell potential. Of course, you need to understand first of all, knowing that in our formula we're saying this is equal to minus NF, right? Well, we do know that N represents the number of electrons being transferred, F represents the Faraday's constant, standard cell potential. Now that we want to make the standard cell potential, the formula, since we already have a Gibbs free energy, so it's going to be minus over NF, right? So now we already know what Faraday's constant is, we already know what that is. We need to now find N. So N is going to be given by looking at the reaction that we have. So for your own information, the reaction that we've been given is also a redox reaction, right? It's a redox reaction. So let me just create space and show how it is a redox reaction. So by redox reaction, this can be split into its half reactions. One of the half reactions is where you have water, right? Of course, giving us oxygen, and then like that. So this is one of the half reactions. And then the other half reaction is the case where you have hydrogen, and then gaining an electron to give us half H2, right? This is what you have. Okay. So now you would want to make sure you balance the number of electrons, right? Since we have 4 there. So 4, 4, and where we have a half, it becomes what? It becomes 2, right? So you have 2. So if you try to look at this equation that we have, what do you expect to come out in this case? So you notice that this may cancel, the number of electrons also cancel. So you remain with oxygen and hydrogen on the right hand side. So what I've written is basically the opposite. So these reactions were supposed to be the opposite. The one down is supposed to be the one reducing, and the one on top is supposed to be the one being oxidized. Okay. So now this is what we're trying to say. So what is important for us, what we're interested in, is understanding the number of electrons that are going to be what? That are going to be transferred. And then you go back to your standard Gibbs free energy, right? Which you know it is dependent on the number of electrons being transferred, Faraday's constant. And then we're trying to calculate the standard cell potential. So you make it a subject, and we said it's going to be our Gibbs free energy divided by what? Divided by number of electrons, Faraday's constant. So get the given value there. Negative 474 over, of course there's a negative here as well. So on the bottom there's a negative. Remember that's where it's coming from, it's in the formula there. So over minus again, the number of electrons are 4. Faraday's constant 96,485. Right. So 474 divided by 4 multiplied by 96,485. So what value do I have? So I'm going to multiply by 1,000 because of the kilo there that we have. So the value that I'm getting is 1.23. What are the units for standard cell potential? Joules, right? The joules? No, watts. It's electromotive force. So this is what we have. Okay, so in summary, what we've talked about is we've said the maximum work done is equivalent to the Gibbs free energy, right? Very, very important. And just know the formula, and the constants are always going to be given in your assessments.
Just a quick summary about the electrochemical series. So, of course, we are talking about the negative, let me say, the reduction potentials of these different metals. Okay, so before we could get to talk about them and understand what these values actually represent, we need to understand what a reducing agent and an oxidizing agent are. So, what are these? So, a reducing agent, as the term entails, these are species or metals or elements that reduce other elements. Of course, the other side, as expected, oxidize. Now, what does that mean to oxidize? What does it mean to, I hope a term is said there. So, what does it mean to reduce? So, to reduce basically involves to gain electrons. So, when an element is gaining electrons, it is said to be reduced. Oxidizing is loss. So, loss of electrons. So, if you have two species, let's say zinc and copper, right? And then zinc loses electrons. So, zinc in such a case is said to be oxidized, and then copper is said to be reduced after gaining. Now, one thing that you need to understand is copper being the one reduced tells us that zinc is the reducing agent because it has reduced copper. Copper being reduced has oxidized zinc, so it is the oxidizing agent. So with that clarity and understanding, these values that we're able to see, I've said they represent the reduction potentials. So informally, I can talk about it informally to help you understand, of course. Um, reduction potential. So think of it as the potential of something to be reduced, right? And then you understand that the positive values actually are bigger. Positive values are bigger as compared to the negative values. Okay. So what does that basically mean? What point am I trying to make? I'm trying to say the positive values are bigger, the negative values are lower. And then these are representing reduction potential. So meaning that the values that are more positive here have got a higher ability of being reduced. The chances of it being reduced are higher. And then the ones that are negative, that are having negative reduction potentials, have got a tendency of being oxidized. So what does that mean? So we've explained these terms already. So these ones that have got negative potentials, negative reduction potentials, are expected most of the times to oxidize. Then the others not to oxidize, to be oxidized actually. So they usually oxidizing, we said, is slow. So they usually lose electrons, and then these ones usually gain. Okay. So in case you don't want to be confused, you can use oil and lead to help you remember. So oil, that is oxidation, is loss, and then lead, that is reduction, is actually gain of electrons. So with that understanding, I believe we are more than capable to just like move on to the other parts, right? Okay. So the other thing that you have to note is every time we are talking about, let's say, what if some of you may be asking questions, what if we are talking about the negative values? So even if you get two negative values, you get them, the one that is more negative will donate, and then the one that is a bit less negative will gain. That is the way it is. That's what these values actually mean and represent. Now, when you basically get to form a cell, you have a combination of these. Let me give you an example. Let's say we have a combination of zinc and copper, right? Let's say we have zinc and copper. So if you look at zinc, where is zinc? Zinc is there. So zinc, we have, I'll write it. We have zinc 2 plus 2 electrons, giving us zinc. The reduction potential is negative 0.76 volts. And then for copper 2 plus. So if you check the way the equations are written, they are all written in the form of gaining electrons, meaning that they are all representing reaction. Okay. So copper is positive. So I said the ones that are negative tend to be oxidized. Okay. So each case you want to come up with the values in the way that you'll be able to form a galvanic cell. So a galvanic cell is a cell that has got a positive standard cell potential. So that is only attained if you basically get to add these values, they give you a positive. So the only way we can ensure that our standard cell potential will be positive is by reversing what? The first reaction. So that we can start with zinc solid, giving us zinc 2 plus. So when the electrons are appearing on the right hand side of an equation, that is an indication that it is an oxidation reaction. Okay, that is loss of electrons. When they're appearing on the reactants part, it shows they are being gained. So after reversing, the value of the standard reduction potential changes the sign. That is very important for you to know that. So in this case, the value has been reversed. Now to get the standard cell potential or the voltage or the maximum voltage that will be produced by this cell with that arrangement, we can add 0.34 and 0.76. So this cell will give us 1.10 volts. Okay, very important. So in a case where you get two negative values, let's say we add zinc and iron, still zinc has got a more negative value. So if we reverse it, we get a positive value. Okay. In a case where you have got two positive values, get the lower one, reverse it. So we'll reverse copper for that case if we're comparing against against silver. Copper will be the one to be reversed so that we get a positive cell potential. So when it comes to the galvanic cell, in this case, zinc will be on the anode, copper will be on the cathode. Anode in a galvanic cell, that is where there are loss of electrons, and that is where oxidation occurs. Copper will be reduced by gaining the electrons from zinc. So one thing that I need to mention is, let's assume maybe zinc had like 4 electrons. That's just an assumption. Now, if there is a reaction happening between copper and zinc, we need to ensure that even in the copper half cell, there should also be 4 electrons. So that would require us to multiply the entire equation by 2. Now, one thing that I want you to understand, that even if you multiply the entire equation by 2, or any equation that represents a reduction potential, after you multiply, the value of the reduction potential does not change. You don't multiply it by the same coefficient. Okay, that's very important. Okay, so the value of the standard cell potential is not affected by the number of electrons. Even if you multiply this equation, for example, that value will still remain as it is. The only thing that happens to it is it only changes if you get to reverse the reaction. Now, in summary, this is what we've said. Metals at the top of the series are good at giving away electrons. These ones that are negative, they are good at giving away electrons, meaning that they are good at being oxidized. So the ones that oxidize are the ones now that reduce others. So they are good reducing reagents because they tend to reduce the others that are down. So the reducing ability of metals increases as you go up these series. Okay. Metal ions at the bottom are good at picking up electrons. They usually tend to gain, so they are easily reduced. So them being reduced, they tend to oxidize the other metals that are on top. That's the summary of everything we've talked about here. So we just need a quick review of what we've talked about so far. So we've learned about oxidation and reduction, where we're saying oxidation is loss of electrons, and then reduction is gain of electrons. So we've said if something is oxidized, then it is called the reducing agent. We talked about a case where we've got copper reacting with zinc. We saw that zinc gets oxidized. Okay, so what that means is zinc is going to lose electrons, and after losing, on the other side, it basically becomes positive. In other terms, you can observe oxidation by an increase in the oxidation number. Copper will reduce because it gains the electrons from zinc. So in this case, we can say copper has been reduced. Okay, now copper has been reduced. It is the oxidizing agent because it has oxidized zinc. So zinc is oxidized. So since zinc is oxidized, it is a reducing agent because it has reduced copper. Okay, that's what we've talked about so far. Now we've also talked about what we are calling a galvanic cell. Now a galvanic cell is basically a cell where we expect that it will be spontaneous. We expect a spontaneous reaction to occur. So what is a spontaneous reaction? So in a spontaneous reaction, first of all, a few things that we expect is the standard cell potential. Standard cell potential is positive. Now, by the way, the standard cell potential occurs at the following conditions. If you're talking about the temperature, the standard temperature is 25 degrees Celsius, which if we're talking about it in terms of Kelvin is 298 kelvins, which is equivalent to 25 degrees Celsius. And then pressure is 1 atm. If you're talking about the concentration cells, the concentration should be 1 molar concentration. So 1 molar concentration, 1 atm. So in case they ask you to state the standard conditions, those are the three standard, the conditions that make the environment to be standard. Okay. So whenever the cell potential is positive, it is said to be positive. What that means is when you have such a cell, you don't need any current to move the electrons. It's the cells themselves will be able to, the cell itself will be able to provide the voltage required to move the electrons from one side to the other end. That's what it means in spontaneous. Of course, we'll also talk about non-spontaneous as we get to move on, where there's need for you to add electricity from an external source for you to make it possible to the cell to operate. So spontaneous doesn't need any external voltage from outside to make the movement of electrons from the anode to the cathode. Okay. And then the other thing that we've also talked about what we are calling the reduction potentials. These are the values that are given. So I said values that are more negative, like zinc, that have got more negative values, they tend to basically get oxidized, meaning that they tend to lose, and they usually act as an anode where oxidation occurs in a galvanic cell. And then the ones that are usually positive, like the coppers, these are usually what? Gaining. Okay, so each time you have been given two equations, I said you can reverse those equations in a way that after you add their electrode potentials or their reduction potentials, they should be able to give you a positive cell potential. Okay, so a cell potential is calculated as the summation of the reduction potentials of the two cells. Of course, you only get to add if the anode has been reversed and the sign has been changed. Okay, that's what you need to understand. In other terms, if you've not reversed, then you just need to ensure that the cathode will be subtracted by the anode. In short, this negative tends to change the sign of the anode. So if you've already reversed the equation, you need not to add the negative in the formula, just add them up. So the reduction potentials are also called standard electrode potentials. So already you've watched an introductory video that has already told you to say the electrodes these are the surfaces actually that tap into the solution, that are like where electrons, a medium between the transfer of electrons from the wire into the solution there. These are what we call electrodes. So the electrode potential, the standard electrode potential, represents the negative reduction potential. So if you see that term, don't be confused. Don't get confused. Okay. The other thing that you've learned is a concentration cell, which is, if you've not learned, then it's upcoming in one of the videos. But the other thing that I wanted to basically mention is the idea that the standard cell potential occurs at standard conditions, which we already mentioned. Now, later on, you will learn about dealing with non-standard cell potential. So the difference is this one, the symbol is just E cell. Then for the standard, there's more like a degree on top there, kind of like that. So this one, which is non-standard, you'll be using what we call the Nernst equation, which you've learned or you're yet to learn it in the other video. So the Nernst equation is what is used to determine the non-standard cell potential of a given cell. Okay. So basically, this is like a summary of what we've talked about so far, and other things that you are expecting to learn batteries, and talk about fuel cell, talk about electrolysis, talk about the redox titrations and application of redox titrimetry. I think that will be the end of the topic.
In this tutorial, we're just going to go over concentration cells. We'll move on and talk about the next equation as we get to even look at the Q and the K calculations under electrochemistry. So let's get started. So now we've already talked about galvanic cells, right? We said the galvanic cell is also called the vortex cell, and we looked at the part of determining the standard cell potential of a galvanic cell. So now a galvanic cell with a setup where we have the anode and the cathode using the same substance, for example using the same metal, let's say zinc is both the anode and the cathode, and then we get to use different concentrations on one part and the other part. So this is our anode and that is our cathode, right? Of course, imagine the full setup of a galvanic cell. We have our electrodes there, and then we have a wire. So the case where you are using the same metal or the same substance in a galvanic cell, it is called a concentration cell. So a concentration cell is a galvanic cell that uses the same element with different concentrations on two different ends. So now let's try to look at an example on how you need to understand it. So let's say we're using copper 2, right? This is our copper 2, and then that's what we have. Of course, we do know that the reduction potential is 0.34, right? So now what we need to expect is this is on the cathode. So on the other side, we expect to have what? On the anode, we need to expect to have this one, copper 2 plus and then 2 electrons. So of course we said whenever we reverse, the sign of electrode reduction potential is supposed to change, so it will become negative. So now this takes us to a new thing that we need to understand, a new concept. Always, whenever you're looking at a concentration cell, the fact that you have the same reaction as reduction and oxidation, always the standard cell potential is always going to be equivalent to 0. Why? Because the standard reduction potential is not dependent on the concentration. Okay, so wherever one side the concentration is higher, the fact is the standard cell potential is always going to be 0 in a concentration cell. Very, very important for us to understand that. So basically, we now know what a concentration cell is. Now, what basically happens? Which one is the anode? Is it the one with a higher concentration or the one with a lower concentration? So you can look over the Charter's principle to help you understand that better. But I'll give you a simple example, right? Okay. So now what you need to understand is this. This is what we have, of course. We have an electrode there and electrode there. And then this is a wire, right? Okay. So now let's assume let's have an equation here. Let's say we have A and B in a chemical reaction reacting. Of course, let's think of a reversible reaction, right? This reaction is reversible, and then you have C and D as your products. So now what happens when you increase the concentration of A in a chemical reaction? Is it going to favor the forward reaction or the backward reaction? The fact that you are increasing the concentration of A, you are increasing the possibility of these guys colliding, so you are favoring what? The forward reaction. If I decide to increase the concentration of a product C, this is going to favor the backward reaction, and it's going to be working against what? The forward reaction. Okay, this is what we're trying to say. So now, in a case of where we are talking about a single-sided reaction, a forward reaction, and then we have C and D as our products, and then we're trying to talk about this guy as, of course, as the anode, and then we have the cathode there, right? So expect electrons to move from one end to the other side, right? So what happens when you increase the concentration? What happens when you increase the concentration? Or let's say what happens when you have, we have a lower concentration on one side, and then you have a higher concentration on the other side. What should you expect? What do you expect? Where are the electrons going to move from? Okay. So we do know that electrons leaving one end is basically oxidation, right? So we said oxidation is loss of electrons. So what you need to understand is the part where it is lower concentration is going to be the anode, so that oxidation will occur, right? So when oxidation occurs, it means the electrons are going to be moving to the other side. Okay, so let's try to review the same example of copper. So we do understand that in the solution there we have copper 2 plus. Of course, the electrodes are all copper solids, right? Okay, and then we have copper 2 plus in the solution there. So now these electrons that are moving are converting what? The fact that it's oxidation, it means that we are starting with copper, right? To give us copper 2 plus. So it being oxidation is going to be increasing the concentration of what? Copper 2 plus, because we are trying to say this is an oxidation reaction. So this is what we're going to have as our product. So the copper 2 plus ions in this solution are going to be increasing. And then if you look at the other side, it is going to be a reduction reaction, meaning that we have copper 2 plus reacting with the electrons that are coming from what? The other side. So now this will be reducing what? This in the solution and increasing what? The copper solid, until they get to a point where they are of equal concentrations. So that's why electrons are lost from the lower concentration to the higher concentration. So this is the operation of a concentration cell. Okay, very few things to take note of. Okay. Now that we've talked about the concentration cell, let's try to go back to the galvanic cells, right? Where we have got two different concentrations being under study. Okay. So what is the effect of concentration in a normal galvanic cell? We'll go back to thermodynamics, where there is a relation between the non-standard cell potential, non-standard Gibbs free energy, to standard Gibbs free energy. So this is the equation that relates the two, and this is what you have. Okay. So now what you need to understand is, when you look at this equation, your R denotes the gas constant, right? Which is 8.3145. You can take note of that. And then your T denotes the temperature, of course in Kelvin. And then your Q denotes the quotient of the reaction, which explains the effect of concentration on what? On the cell potential. So we understand all those things more in details as we get to move. Okay, so we've talked about the calculation of what we call the Gibbs free energy, and we said it is minus NF watt, right? So the same is for the non-standard, except our E is going to be non-standard, right? So it will be minus F, and then just a cell potential, which is not standard. And then we have RT, and then natural log of Q. Okay, what do you expect at this stage? So we're trying to come up with an equation which will help us calculate the new cell potential when you change your concentration. Remember, we said that our standard cell potential occurs at standard conditions. That is 1 molar concentration, 298 Kelvin or 25 degrees Celsius if you want, and 1 atm. So these are the pressure, temperature, and concentration standards for standard cell potential. Now, calculating this non-standard cell potential implies that the concentration is different from that we have, and of course the temperature may also be different. Sometimes, most of the cases, it's going to be the same. Okay, so we are trying to come up with an equation that will help us do all those calculations. So we're trying to make these be the subjects, so we can divide on both sides everything that we have by that. So now you notice that this part, we're going to remain with first the non-standard cell potential. This part is going to remain with now the standard cell potential, and then you have a negative there, RT over NF, right? Of course, natural log of Q there. So this is now the equation that will help us each case we have been given what? The standard cell potential. We've been given the number of electrons, Faraday's constant, the gas constant. All these three standards. This is going to be determined depending on the reaction that you're given. And then your temperature will also be given. And then your Q will be determined from a given concentration. So look at the calculations of all these. So this is now what you call the Nernst equation. Okay. So now, we've said R is a constant. Faraday's constant is a constant. Temperature may be known in a case where we have a varying what? Well, let's say we have a constant temperature. Let's say we're talking about 298 kelvins, right? Or 25 degrees Celsius. In such a case, it implies that you know what you have. So what you have is your R is 8.3145, all right, and then your temperature 298, and then over what? The Faraday's constant is what? 96,485, and then you have your N there. So I've just gotten this part, and I'm trying to show it there. So 8.3145 multiplied by 298 divided by 96,485. So what I'm getting is what I'm getting after performing all those calculations, I'm getting 0.0257. So remember it was the N down there, so natural log of Q, and then this is the simplified form of equation in terms of the natural log. Whenever you're dealing with what? Whenever you're dealing with 25 degrees Celsius or 298 kelvins. Okay. So now this equation can also be converted to the log. Okay. So when you convert this equation to the log, it becomes 0.0591. Okay. 0.0591 over N, and then it becomes log of Q. So these are the two forms of equations that you can use at 25 degrees Celsius or 298 kelvins with varying what? With varying conditions, of course, that is in terms of concentration and pressure. Okay. So now that we've come up with the next equation, we know the different forms of equations that we can work with at different conditions. Okay. Another important thing for us to understand is that at equilibrium, our Q is considered to be K. So Q and K are just one and the same, except K is Q at what? At equilibrium. So of course, you understand better at equilibrium when you've talked about equilibrium, that is understanding that the forward and the backward reactions occur at the same rate. Okay, the rate at which the products are being formed is the same as the rate at which the reactants are being formed back. So that is what we call equilibrium. And then some few things have to change at equilibrium. At equilibrium, the non-standard cell potential is what? 0. So this guy is 0. And then if this one goes the other side, it will be that. And then you have negative 0.0591 over N, and then you have log K there. So now, these questions are going to require you to be able to calculate your K at equilibrium. Okay. So now, our goal is to make log K the subject, right? So how do you get to do that? So of course, you have 0.0591 over N, and then you have log K. I've just moved my right hand side to the left, and then I've divided by negative on both sides. So you notice that whatever is on top is supposed to be on the bottom the other side. Okay, and then N will be on top. So I've just multiplied by the reciprocal there. I've divided, and that's what we have. So this is now the form of equation that will help you find K in a case where we've given you the standard cell potential and the number of electrons, of course, determined from a given reaction, right? And then what you're going to have is your K. So log means it has base 10, and then it will be 10 raised to the power that. So that is the form that will help us find the equilibrium constant at a given given the standard cell potential and the number of electrons being transferred. Okay, so now let's try to look at an example that will help us just to make some, to make the information that we've learned solid enough so that we are not able to forget. Okay, so now Q, of course, the form of equation that we've talked about, of course, whenever we're dealing at 25 degrees or 298 kelvins, we've said our non-standard cell potential is going to be dependent on the standard cell potential. You subtract 0.0591 over N, and then you have log Q there. So now I want you to understand some of the things here. There are going to be cases where the non-standard cell potential is going to be greater than the standard it can also be less than the standards. Okay, now you need to understand exactly how is that possible. Okay, so what we need to realize is the fact that Q is basically dependent on the concentrations. So of course Q, which is the quotient, the reaction quotient, is only dependent on the aqueous and the gaseous states in a reaction. All solids are ignored, so in this case we'll not consider the solids, we just look at the aqueous states. And in this case it's always going to be products over reactants. Of course the concentrations are supposed to be raised to the stoichiometric powers. In this case we have aluminium, right, as our product. So it's supposed to be raised to the power at 2, which is the stoichiometric coefficient. The other side of manganese is also going to be raised to the power 3 because that is what the stoichiometric coefficient that we have. And then you remove what is inside, you put the concentrations that we have. In this case we have 1.5 for our products, and then for our reactant what we have was 0.5, right? So from there you should be able to find your Q, and then I'll say 1.5 raised to power 2 divided by 0.5 raised to third power. Okay, so what I'm getting is my Q is 18. My Q is 18. Okay. So what is important is we've seen now that our Q is dependent on the products over what? Over the reactants concentrations. Of course these are raised to their stoichiometric powers. Let's use N and maybe N numerator, let's say R. So this is what we are saying. So which implies that when you increase the products, you increase what? You increase the quotient Q there, right? And then when you do the opposite, when you increase the reactants, you reduce Q, quotient Q there. That is what you have. And what does that mean? So what this means is, how is it going to affect our non-standard cell potential? How is it going to be affected by all what we're saying? So when you increase the products or the reactants, so when you increase the reactants, what is happening is you're going to favor what? The forward reaction. You're favoring the forward reaction, okay? Which will mean that the cell potential required will be greater to move the electrons because of what? Of a greater concentration. Now, if you do the opposite, you decide to increase the products. When you increase the products, what you are doing is it's going to be very difficult. It's going to be difficult for, or you're working against the reactions, the movement of electrons. So the standard cell potential or the non-standard cell potential is going to be less than the standard cell potential, and that is that condition there. Okay, so now in this case we will have every information that we need to perform our calculations. Our standard cell potential has already been given to us. In a case where not given, we need to look at the half reactions of the main equation there, and then you look at the reduction potentials, and you should be able to do that, right? Because we said the standard cell potential, of course, is always supposed to be positive for a feasible reaction. That is supposed to be spontaneous. And then 0.0591, our N goes back, takes us back now to the number of electrons that are being transferred. So now this will now help us. That's why it was very, very cardinal of us to just get to understand how we get to split the given reaction. So this is over N. Let's try to see what we have now. So what we have now, of course, that is log 18 in terms of our quotient Q. Look at what we have. So aluminium, 2 aluminium is giving us what? That. So this tells us to say that you're moving from 0, then you're going to 6. So it tells us you have 6 electrons, huh? And then if you also try to write the other one, you also notice that 6 electrons were being gained. So our value of N is what? 6. So what I did is I multiplied these two by that power, which implies that we had positive 6 this side. This side you have a 0 charge. So which implies that since the positive on the right hand side, we had lost electrons, which is oxidation, right? Okay, so you can use any of the half reactions to help you determine the number of electrons, if it's balanced, that is. Okay, so you have 6 electrons. So now, of course, if you look at the information that we have, you should be able to predict the possible result there. Because look at this. Our reactant is 0.5, our product is 1.5. So the standard conditions for that is 1 molar concentration. So now we have a R concentration of the product, which implies that it is working against what? It is working against the actual thing that is supposed to happen of moving to the forward part. So there will be less energy required because the products are already in R concentration. So we should expect this guy to be less than the standard cell potential because of the fact that we have a higher concentration of what? The products. So now try to perform the calculation. 0.0, of course, we'll start with log 18, and then I'll multiply that by 0.0591, divide by 6, and then subtract from 0.48. So what I'm getting is 0.46 0.47 volts, which is basically less than the standard cell potential. This is what we have as a non-standard cell potential, and this is how helpful this equation is. Okay, we call it the Nernst equation. It helps us to perform calculations for the non-standard cell potential at given temperature and given concentrations of the reactants and the products. So I'm sure now that you're able to perform various calculations to deal with K and Q at given temperatures without any difficulties. Thank you very much for taking time to watch, and have a blessed day.
Are you enjoying this video lesson? So you can actually access the entire topic you are watching or the entire practice questions of a video that you may be watching right now. So if you go to our website is transcendedinstitute.net. Okay, so there are 3 ways that you can access our videos. So you can use Patreon, you can use channel memberships. If you're in a country where it's allowed, you'll be able to access our full topic videos and full practice questions. So alternatively, you can access the videos using our learning portal. The link is learn.transcendedinstitute.net. So I'll show you a few videos that you can have access to after registering. So for example, if you had to open mathematics as at now, these topics are the ones that are available, which you can learn from scratch. I can just give you an idea of, so you like learn everything from scratch, meaning that even if you're learning something for the first time, these videos are there to help you with concepts as well as practice questions. So for example, these are tutorial sheet solutions from different tutorial sheets, which can help you as well get to learn faster and remember. So binomial as well, there it is. And of course, this applies to all these other topics that are available. Trigonometry as well, calculus, depending on the topic that you're interested in mathematics. So you can just head over to the site at now to check what is currently available. Even without registering, you should be able to see the content in each topic. So let's assume you're interested in physics. These are the topics available as at now. So if you open chemistry, these are the topics available as at now: electrochemistry, stoichiometry, thermochemistry, kinetics, equilibrium, solubility, equilibrium, atomic structure. So trust me, if you open these videos, you might have learned the topic in full. Let me show you stoichiometry. So stoichiometry, we have all the way up to 21 videos, including the tutorial sheet solutions, which will help you to practice both the concepts and also prepare for questions. Okay, so feel free to head over to the site and check out these videos on your own. So equally biology videos are also available, which you can also basically get to access. So these are the topics available so far. Yeah, so pretty much these are the ways you can easily access our full membership videos that you don't have access to on the channel.
In this tutorial, we're just going to answer a very interesting question from the Nernst equation. So I'm sure if you look at the question, you're able to say it's very simple. So Of course, I'm assuming you've done a lot of things under electrochemistry and you're already acquainted with the Nernst equation. Okay, so the Nernst equation, this is the equation that helps us to find the non-standard cell potential when you are given the standard cell potential, and then of course R is a constant. You are given the temperature, the number of electrons, and also a Faraday's constant, and then the natural log of our quotient Q. So all these things should be available. Okay, so Q is determined using the concentrations, and then Faraday's constant is a constant. So constant temperature is given. N is determined from the half reactions given. E is calculated from the reduction potentials, and also sometimes it's calculated using the non-standard cell potential if it is given. Okay, so these are the few things that you need to know with this equation. Okay, and then at 25 or 298 kelvins, we do know that our formula is simplified to something simple, where we now just have 0.0592 over N and then log of Q. So now if you look at the question, we've been told the EMF of the cell at that temperature is that. So we've been given the EMF. Also, now is it standard or non-standard? So looking at the conditions, of course, for something to be at standard, of course, for the standard, for us to have a standard cell potential, the conditions are 298 kelvins, 1 atm, and what? And 1 molar concentrations of the reactants and the products. So in this case, if you look at the concentrations that we have, they are not standard, right? So it's non-standard cell potential. So the electromotive force given us is non-standard. Now, what do they want us to calculate? They want us to determine the equilibrium constant. So equilibrium constant, we do know that at equilibrium constant, the non-standard cell potential is 0, and then the standard we are supposed to calculate from what we have. So this will be the remaining part of a form of equation when we are dealing with what? So log of k when we are dealing with the equilibrium constant. So we want to find the value of k. So notice that we would need to use the value of a standard cell potential. So we would need to calculate it beforehand. Going back to our equation. So our non-standard cell potential has been given to be 0.2905 equal to our standard cell potential is what we're trying to find. So the number of electrons, so this one is very easy for you to tell. So oxidation was from zinc to what? Reduction was from iron 2 to iron. So I'm sure you're able to tell that is the difference of two electrons being lost, 2 electrons being gained, right? So no need of us balancing anything, we just have to substitute directly. So we'll say over 2, and then now log Q. So what is our Q? Let me just write down the half reactions to help you understand. So the fact that zinc is written first is on the anode, so it's being the one oxidized. So 2 electrons were being gained to give us zinc 2 plus. And then for the iron 2, we expect the opposite. Iron 2 was being what? Was actually being reduced. So there's something wrong there. Zinc is being oxidized, electrons are supposed to be lost. So for the iron 2 to gain and then become the iron solid metal. Okay, so oxidation is loss of electrons, and then reduction is gain of electrons. So that if you add the positive and the minus 2 to give you a 0, so that's what we're trying to say. So now in this case, our goal is to come up with a balanced equation. So the electrons will cancel out. So what you notice is zinc 2 plus is what? Is a product, and then the iron 2 is our reactant. So those are the things of our interest here. So Q is always going to be given in terms of the reactants and the products. So it's products over reactants, of course raised to stoichiometric powers. Okay, so we're saying our Q is in terms of products over what? Over reactants. So if you're able to remember what from showing, zinc is the one that was on the product, zinc 2 plus. So whenever you're trying to find constants of any given reactants or any given reactions, you basically don't look at the liquids and the solids. You just look at the gaseous states and the aqueous states. So in this case, we just have aqueous. So, and if you notice, we are the only ones that have been given concentrations. So zinc 2 plus being our product, 0.01. So if it had a stoichiometric coefficient of 2, maybe that is going to be in a case where if there was any need of balancing, it was going to be the power 2. So if you've done chemical equilibrium, it makes sense. If you've not, don't worry, it will make sense as you get there. So you have divided by the reactant, which was 0.01 as well. It just has a stoichiometric coefficient of a 1 as well. So they are all raised to the power 1s. And then if you get to divide these guys, you notice that they're going to give us 10. Of course, I've written the units here deliberately to show you that the constant of a reaction doesn't have any units because we will divide, so it's more like a ratio. So we have 10, so our Q is equal to 10, and then we can just substitute in the given equation. So from there we can find now our standard cell potential. So you want to get 0.0592, we are dividing by 2, and then multiplying by the log of what? Multiplying by the log of 10. Okay, so log 10 multiplied by 0.0296. So of course log 10 we do understand that we're not really supposed to perform anything here because this gives us a 1 straight away from our logarithms. So the other side, 0.905 plus 0.0296 is equal to the standard cell potential. So you want to add that to the 0.2905, right? So our standard cell potential is equivalent to 0.3201 volts. So we now have our standard cell potential. We can now go back to the equation. So we do know that whenever we're trying to talk about the equilibrium, what is different or unique about it is the non-standard is equivalent to a 0. Okay, and when Q becomes K, so let me just make those changes here. So that is 0, and then Q is K. So that's what we're trying to find, K. So if you try to make it the subject, it goes the other side as 0.0592 over n log K. So this negative has become a positive, equal to standard cell potential. So of course you want to multiply by the reciprocal of the fraction, so n over 0.0592, so that these will cancel out. So the same the other side, n on top, and then on the bottom 0.0592. Remember, whatever you do to the left should be done to the right hand side as well. So I'm sure for you to reach to this at this stage, you are following up and you're understanding. So I've got a couple of videos that you can get to access after registering with Transcended Institute. Electrochemistry has got a lot of videos from the introduction of the galvanic cells, going up to the Nernst equation, electroplating, and many more things. From there, the other topics have been covered as well, things like thermodynamics, talking about chemical kinetics, organic chemistry. So make sure you get registered. The link is in the description, and you'll be able to access these tutorials on our platform online just upon making payments. Okay, let's continue. So now at this point we have our standard cell potential, and then we have n. So n still represents the number of electrons that were being lost again in the reaction. So we just want to substitute now and then see what we're going to have. So our log of K is going to be n is the number of electrons, and then the standard cell potential, which we've calculated, is that 0.3201 over what? So there's 0.0592 on the bottom, 0.0592 592. So of course we do know that log has got a base of 10 there, so our k is going to be 10 the power. So we can multiply what we have on the on top. 2 times 0.3201 divided by 0.0592. So I'm getting a value of 10.81. 10.81. So 10 to the that power, what do you expect to be the actual value? So even at this point it can still be marked. So 10 to that power of something like 6.52 times 10 to the power 10. Of course it has got no units, so don't stress yourself, just like I showed that Q doesn't have any units because it's more like a ratio. Yeah, so that's it for this video. Very important key concepts is make sure you're able to identify the kind of the cell potential that we've given you. Is it standard or non-standard from looking at the conditions that were provided? Of course, unless it is explicitly stated to say it is a standard cell potential, don't consider it to be standard unless if all the conditions are matching up. Okay, so thank you very much once more for watching. Make sure you register to get to access many more tutorials on electrochemistry and other topics.
We've previously talked about what concentration cells are, but we didn't look at calculations. So first of all, just a quick review. What is a concentration cell? So a concentration cell is equally an electrolytic cell with 2 electrodes or 2 half cells as usual. And then the only difference from the galvanic cell is that the electrodes are the same. So that's a key concept about the concentration cells, same electrode. So you understand that we're not talking about an electrode, we're talking about the part that touches the solution, or the metal part that connects to the wire. So on the anode and the cathode, what you're saying is the electrodes are the same. So that's what a concentration cell is. So what basically tends to happen is we can consider a case where we may have, let's say, copper, right? Copper 2 plus in both solutions, meaning that obviously the electrodes were expected to be the solid copper. So what creates the difference, or the potential difference, is the concentration. So where you have a lower concentration, and then the other side has got the higher concentration. So what basically gets to happen in a concentration cell is electrons will move from where there is lower concentration to where there is what? A higher concentration. So in this case, electrons will move from the left to the right. So where there is a lower concentration, we can take that to be our anode, and then where there is a higher concentration, that can be taken to be the cathode. So what basically happens is we understand that at the anode, that's where oxidation does what? Occur. At the cathode, that's where reduction will basically get to occur. So why is it so? So what basically happens is, if I was to write the equation there, we understand that on the oxidation part, we expect that the copper solid is basically going to produce a copper 2 plus ion, and then basically getting to emit the 2 electrons. Now, one thing that we understand is that concentration always refers to the aqueous part. So obviously the ions, that's what the concentration is referring to. So if we are saying initially the concentration of 0.01, now we've seen that after oxidation there is production of the ions. So we expect that as the reaction progresses, there will be an increase in the concentration on the anode, and then on the other side where there's reduction, the copper 2 plus ions in the solution, they will be gaining the 2 electrons coming from the other side of lower concentration, giving us more of the solid metal on the electrode. So this will reduce the concentration. The concentration on the other side will be reducing. So this will continue, electrons will continue flowing until equilibrium is established. So at equilibrium, that is a point where the concentration on the anode and the cathode are basically equal. So here is an example of a concentration cell. So we've seen where there is a lower concentration, electrons will move towards the part where there's a higher concentration. So that I've explained how and what basically makes that to happen. The reason is simple. So that where there is less concentration, oxidation will occur. So understand that oxidation leads to an increase of the ions in the solution, and then reduction reduces the ions in the concentration and leads to a conversion to a solid. Okay, so basically that's what we are trying to say about a concentration cell. So the electrodes on the anode and the cathode are basically the same. I've given you an example. It can be zinc on both sides. In the solution, same electrolyte or same ions. Let's look at the practice question. So with an understanding of what a concentration cell is, are we able to answer the questions? So the other thing that you would want to just think about is, if I take you back here, and then let's say we had copper, right? So if we had copper in one case, so the copper solid emitting copper 2 plus ions with 2 electrons, and then on the other side we expect that the copper 2 plus ions in the solution will gain the 2 electrons and get to become solid, right? So we understand that the cell potential of copper, the reduction cell potential is negative 0.34. So we expect that in the other side it will be a positive value. So assuming you want to determine your E cell, your standard cell potential, if you basically get to add the two values, you get a 0 at voltage. So the standard cell potential in a concentration cell, because we are using the same electrodes on the left and the right, it will be 0. So then how do we basically get to calculate the non-standard cell potential, where the question is just saying calculate the cell potential for the concentration cell with 2 silver electrodes with different concentrations given? So I've already talked about the Nernst equation previously in the earlier on. We talked about that. So the next equation, of course, comes from the relation between the Gibbs free energy, the non-standard and the standard. So the non-standard cell potential is equal to the standard cell potential minus 0.0592 over n log of Q. So of course there are two forms of this equation that I've already explained earlier. So we'll use this equation to just simplify things. So the n there basically denotes the number of electrons that are being transferred. The quotient there looks at the ratio between the concentrations, and then this is the standard cell potential, and then this is what we're trying to find, the cell potential. So we've said the standard cell potential in a concentration cell is 0. What's the number of electrons that were being transferred? So if you write the half cell, okay, so we just said the half cells are the same in this kind of reaction, right? So we expect that there will be emission of 2 electrons, giving us silver 2 plus ions, and then we have 2 electrons emitted. So here the number of electrons we're dealing with is 2 log of Q. Now what is Q? Now that is where you have to pay particular attention. So when it comes to Q calculations, so this is going to make more sense as you basically get to study chemical equilibrium. Okay, so I'll give you a very simple example to just guide you. So let's say you have A plus B, B, giving you C, C plus D, D. That as the reaction there, right? So what you expect is your Q or your K, which I've also explained a bit earlier, is basically equal to, so the easiest way you can remember this is its products over reactants. So your products, so this is of course dependent on the concentration. That's why I'm using those brackets to show that we are studying concentration. So, and then divided by that, the product of the reactants. Now these are supposed to be raised to the stoichiometric coefficients. So C will be raised to their stoichiometric coefficients. I'm using small letters to denote their coefficients. So that means that if you had 2C over something, 2 plus ions, it means that this C over ion is supposed to be raised to the power 2. Okay, that's basically what we're trying to say. Now, what you get to add in this equation, you only include the aqueous and what? And the gaseous. You don't basically get to include the solids and the liquids because we are dealing with concentrations here. Okay. So going back to our question there, we've seen that we're dealing with the same half cell, right? We are dealing with the same half cell. So on the left and the right hand side, we've got the same. So let me try to write the other reverse form of this equation. So it would be Ag2 plus ions plus 2 electrons, giving us what? Now the question is, which one is the anode, which one is the cathode? So which one is oxidation? Oxidation is loss of electrons. So this is the anode. And then on the bottom, that's the cathode. Now what have we said? What have we said? So we've said the anode is basically where we have got what? A lower concentration. So therefore, where we've got a lower concentration is where we have 0.02. And then the cathode is where we've got a higher concentration, 3.0 molar concentration. So what do we expect to have? Which one is the product? Which one is the reactant? So remember, when we're dealing with Q calculations, we are only focusing on the aqueous and the gaseous state. So the solids will basically be all ignored. Okay. So meaning that this Ag2 plus is on the product side, which is having a 0.02. Okay. So therefore, what we expect is 0.02 divided by 3. Those are the two concentrations. Now, what are their stoichiometric coefficients? So if you get to balance up these and form the balanced redox reaction, you'll notice that they'll all be having a coefficient of a 1. So no need of us basically raising them to any powers, because even if we raise them to 1s, nothing will change. So I had to write that because the concentration cell is a bit tricky when it comes to trying to understand basically. So the basic idea is the lower one on top, the higher one down. The reason is simple. The lower one, that is where oxidation basically gets to happen, and in oxidation the ions are on the product side. Okay, so let's try to perform the calculation that we see what we're going to have. So I like starting with a log part. So divide 0.02 by 3, and then the log of it, log of the answer, multiply by 0.0592 divided by 2. So the answer is positive because the log part gave us a negative. So it's 0.0644 volts. Okay. So if you're trying to assess what you've been given, your answer may just as n 0.06 volts. So this is an example about concentration cells calculations. So understand what a concentration cell, practice more questions to deal with the next equation, then you'll be able to attain confidence. I'll just introduce what batteries are. So what's a battery? So a battery is an electrochemical cell that is basically used to store chemical energy and produces electrical energy when required to. Okay, So you can basically think of it to be a series of two or more electrochemical cells used to store chemical energy to produce, I can say, so used to store chemical energy and produces electrical energy. That's the way we can think about it in simpler terms. So we already know of the uses of a battery. Okay, so batteries are used in electronics, things like a phone. They use what? Batteries. Think about vehicles. They also use batteries. There are a lot of things that use batteries. You can also think of what can you think about? Calculators. They all use batteries. Now we need to understand the concept of an ideal battery. So an ideal battery, of course, the word ideal means the best state or the most desirable kind of a battery. Okay, so ideals are not actually the reality, but what's the best form of a battery we could ever have. So the desirable battery should never run down. Okay, it should just continuously be providing voltage. And then an ideal battery should produce unchanging voltage. Okay, meaning that the rate should still be the same, the voltage should still be the same, the voltage being provided. And then it should be capable of withstanding environmental extremes like heat and humidity, so that even in bad weather conditions it should still be able to stand. Okay, but in reality, as people usually say, reality is often disappointing. So in reality, batteries are basically created to balance between the desirables, of course, of an ideal battery, balancing up with a practical application or practical limitations. So for example, if you look at the use of a car battery, if you are to use a car battery on the on your phone, it may not actually run out. Okay, it may not actually run out, so it will be an ideal battery, but again you need to balance it with practical limitations. Just think about it. So looking at the mobility of a phone is designed for you to move with it. So who would manage moving a phone with a battery as big as a car battery? So we are trying to balance between the practical application and the ideal. So that's why small batteries instead are used. Even if they run out, it's better off than having the battery that will make it so heavy that people will not even be able to carry it, even if it will continuously provide the required power. Okay, so basically this is an introduction to what a battery is. There are two kinds of batteries classified as primary and secondary. So what's the difference between the two? So the simple difference is the primary battery is a single use battery. Okay, single use battery. So I think calling it a single use may mislead, but the basic concept is a primary battery cannot be recharged. Secondary, these are batteries that are rechargeable. Batteries in the phone, batteries, car batteries, those are rechargeable batteries. But there are batteries like, for example, the ones that are used in a calculator, in watches, they are not rechargeable. So those are examples of primary batteries. So let's proceed and get to talk about some of examples of the types of batteries that are there. We've been discussing galvanic cells, so let's now talk about electrolysis. So basically, we can think of electrolysis to be the process where we have an ionic compound decomposing into its elements by passing through a DC current. So, for example, you can think about sodium chloride. Electrolysis is the process where we're going to break or decompose this compound into its elements. In this case, we know it is made up of sodium and chloride ions, of course. So that process of breaking this up is electrolysis. Now it is done by using an external power source, which we are calling, of course, DC, okay, direct current. Now this is what makes it different. This is what makes electrolysis different from the process that occurs in a galvanic cell or a Redox cell. So the kind of a cell where electrolysis occurs, we call it an electrolytic cell, coming from the word electrolysis itself. So electrolytic cell is the cell where electrolysis occurs. So we have a decomposition of a compound into its elements by passing through a DC current. So the DC current basically is supposed to be passed through an electrolytic cell. So what you're seeing on the right here is basically an example of an electrolytic cell. So just like in a galvanic cell, even here we expect that oxidation will still occur at the anode, and then of course at the cathode, that's where we're going to have reduction. Now if you think that you need to take note of under an electrolytic cell is the anode is connected on the positive terminal of the power source, the cathode is the negative part of the power source. Okay, so this being the case, I've said oxidation occurs at the anode. So oxidation, we said, is loss of electrons. So we expect that again in this case we'll have electrons moving from the anode to the cathode. So if we look at the diagram that we have on our right here, the part which is connected to the positive terminal is this side. So this electrode is going to be called the anode, because I've said the anode is connected to the positive terminal. Okay, and then of course on the other side the cathode is connected to the negative part of the power source. Okay, so which implies that in an electrolytic cell we have electrons moving from the positive part to the negative part. Okay, so that is like a force. We're forcing things, we're forcing electrons to move. They don't flow naturally, so we call that a non-spontaneous reaction. If you're able to remember, under a galvanic cell we said the reaction is spontaneous, meaning that it occurs naturally without usage of an external power source. Okay, now in this case it is non-spontaneous because we have to use an external current to move or force electrons to move from the positive part to the negative part. Now, in addition to the electrodes, which are representing the cathode and the anode, we also have what we call an electrolyte. Okay, so we have what we call an electrolyte. So I believe you know what an electrolyte is. In simpler terms, an electrolyte is basically any substance that conducts electricity when dissolved in water. So you can think about sodium chloride as our example in this case. So in this case we use sodium chloride to demonstrate what basically occurs in an electrolytic cell. So sodium chloride dissolved in water is the solution that we have here. So after it is dissolved in water, you realize that sodium breaks down into sodium ions and chloride ions. So the entire equation that we are thinking about in this case is sodium chloride being broken down into sodium plus, and then all these are in aqueous state. So that is what we have there. So take note that the positive ions are being represented by the positives in our diagram there. Okay, so now I want you to know that the positive ions, something like sodium, Okay, they are referred to as anions in our textbooks. So anions, and then of course the negatively charged, the chlorides, these are called cations. Okay, so cations will be attracted to what? To the cathode, anions on the anode. Now one thing that you need to understand is in chemistry, a positive sign indicates that that element has lost what? Has lost or donated electrons. So meaning that the sodium ion is has lost. And then the chloride in its negative, when it's having a negative charge, this usually happens to non-metals. A negative charge indicates that there was gain of electrons, meaning that it is not existing. All these anions and cations are not existing in the natural state of the element itself. So after electrolysis, we expect that these are supposed to go back to their natural form. So how does that happen? So what happens is the positive charged ions are expected to be where? So if you look at it, first of all, you understand that it is a positive part, positively charged, right? So positively charged indicates it has lost electrons. So meaning that in this case, for it to be neutralized back to its original form, it will need to basically gain an electron, right? So where do we have electrons flowing to? So we know that electrons are flowing from the anode to the cathode. So therefore, the positive ions are going to be on the cathode, okay, so that they can receive electrons coming from the other side, the anode. So on the anode, we've got the negatively charged ions. So why is this so? The negatively charged ions in this cell are basically going to donate the electrons to the anode, okay? And then, so that is basically oxidation. I can even show now the actual reaction that's going to occur there. So for oxidation, we have the negatively charged ion. In this case, we're using chloride as an example. The chloride ion is basically going to do what? It's going to donate an electron, okay, giving us it will go back now in its natural form because the negative electron has been lost. Now, because there will be many of the chloride atoms being formed on that electrode, we expect that since chlorine naturally exists diatomically, it's supposed to react with another one so that it forms a chloride gas. Okay, and then for the reduction, which will happen to the positively charged ions, what we expect is for reduction, we'll have the sodium ion, in this case, gaining an electron which has come from the anode to give us sodium in a solid form or metal. Okay, so this basically is like a summary of what basically happens. So oxidation, just like in a galvanic cell, occurs at the anode. Reduction occurs at the cathode. Now in this case, the anode should always be connected to the positive part, and then we've got the forcing of electrons flowing from the anode to the cathode, and the anode, which is positively charged, attracts negatively charged ions, which basically donate electrons, which are the electrons which flow to the cathode. And on the cathode there, we've got the positively charged ions, which now gain the electrons flowing from the anode to be neutralized back to their natural elementary or state or form. So we have an electrolyte, of course. We have an ionic compound dissolved in water being split into its ions. So that's basically the summary of what happens in terms of electrolysis. Okay, so with that understanding, we've also, of course, we need to not forget that it's non-spontaneous reaction. So some of the applications of electrolytic cells are as follows. So we have production of oxygen gas and hydrogen gas from water. This process is also used for extracting aluminium from its ore, bauxite. This is also used in electroplating, which is a process of forming a thin protective layer of a specific metal on the surface of another metal, and then we also use it in the industrial production of high purity copper, zinc, aluminium. Okay, so it is almost always done using the process of electrolysis. Okay, so basically this is an important summary of basics of an electrolytic cell. At this point, we've already talked about electrolysis, and we've talked about how it happens. So one of its basic applications is electroplating. So electroplating is basically the depositing of a metal at the cathode. So we already established to say, in terms of an electrolytic cell, of course we know that there is usage of DC current and from an external source. So electrons as well, they move from the anode to the cathode. Okay, so understand that the electrons that go to the cathode, basically they get to react with the, we'll call them what, the ones that are positively charged, the positive ions, so that they basically get to be neutralized. So I'm giving an example of sodium, right? It will gain back an electron because the positive sign indicates that it had lost. Okay, so now what we are saying is, what this solid that is being formed will be deposited on the cathode. So that process is what we call electroplating. Now what we want to understand basically is how we get to determine how much of it has been deposited. Of course, applying the Faraday's laws, where we know that time has got an effect, the voltage has got an effect, so all those things are to be applied here. So we use this information given to predict or determine how much of the mass will be deposited on the cathode. So in this case, we are looking at copper. So copper 2 plus is reduced. So copper is reduced by gaining 2 electrons, obviously, so that it gives us copper solid, right? Okay. So 2 electrons are the ones basically that are what gained in this case, since it's copper 2. And then if a current of 1.25 ampere is passed for 72 hours, what mass of copper is deposited at the electrode? Assume 100% current efficiency. The atomic weight of copper has been given. So a few basic steps. Each time you're looking at such a question, think of it in terms of charge, right? So think of it in terms of charge, which is denoted by Q, right? So we'll try to determine our charge. So Q is basically IT. Okay, so charge is basically the flow of current in a wire. So you are looking at it, the rate of flow. So you're looking at it in terms of a current, and then you've got the time. Okay, so charge is a product of current and time. So with that understanding, in this case our current has been given to be 1.25 ampere, and then we have time. Okay, so the time we've been told 72 hours. So now what you need to understand is the fact that ampere is the same as coulomb per what? Per second. That's why we say current is actually the rate of flow of what? Of charge. Okay. So coulomb per second. So we need our time to be in seconds. Now we've been given 72 hours. Now we understand that in an hour you have how many minutes? You have 60 minutes. Now in every minute you have what? You have 60 seconds. So if we are to determine how many seconds are in an hour, we would have to say 60 times 60, right? So we have 3600 seconds in an hour. Okay, So if that's the case, how do you convert the 72 hours? So we need our seconds to be on top, right? Okay, we need our seconds to be on top. So say 3600 seconds per every hour, and then multiply by 72 hours. Okay, so at this point we expect that the seconds here will cancel, the hour will cancel. So we're able to find now the only unit that is remaining there is the coulomb, if that's the correct pronunciation. So we have 1.25 multiplying 3600 multiplying 72. So what we have at this point is 324,000 coulomb. Okay, so we determine the charge by using the current and have you raised that current and the time. So in terms of now determining the mass that is going to be deposited, we need now to use the Faraday's constant. So the Faraday's constant, the value is 96,485. That's the value of the Faraday's constant. Now what else do we basically get to work with? So we've been given the molar mass itself. Okay, so it's very important that we basically get to understand the units of Faraday's constant. So the units are coulomb per mole. So why am I focusing on the units? I'm focusing on the units because these are going to help us. Okay, so with that understanding, since we want to find the mass, we're interested in that our final unit remaining should be grams. Now the coulomb. So with the charge that we've calculated, I need also to mention that if you look at the Faraday's constant, the units are per mole of actually electrons. I needed to mention that. So in terms of multiplying with this part, we need to work with dimensional analysis by looking at the units. That's the best way of handling it. Okay, so obviously we expect that when it comes to the coulomb, it's on top for the Faraday's constant, so it has to go down. So the more of electron will go on top, so more like we are dividing, right? So more of electron on top, and then we have the Faraday's constant on the bottom. So that is coulombs. So we can cancel those units already. The coulombs have gone away. Now we need to cancel out the more of electron. How do we handle that? So we need to multiply by something that will help us do away with the more of electron. But let's not forget that our goal is to find the mass. So let me first go upon something that will give us the mass. So we're dealing with copper. So its molar mass will give us a mass on top. So 63.546 grams per mole. Now that mole, I need to indicate that it's a mole of copper. Okay, per every mole of copper, there's 63.546 grams. Okay, what else do we need? Now we need to pay attention again to the actual equation. So you can observe actually that there are two electrons, these two electrons, okay, two electrons that are being produced, that are being gained per every mole of one copper formed. Okay, so now check that the mole of electron is on top there, so we have to have it down. So we have 2 moles of electron per every mole of copper solid formed. So you realize that this is now making sense because we expect that the mole of electron will cancel with that mole of electron, the mole of copper will cancel with this mole of copper. So the only unit that is remaining is what? The grams there for the mass. So if I grab my calculator there, beginning with a charge 324,000, okay, 324,000 divided by, first, okay, let me multiply first of all by 63.546, and then we divide by what's on the bottom. On the bottom we've got the Faraday's constant, 96,485, and then a 2 as well. So the value that I'm getting here is 106.7 grams. So that's the expected mass of what? Of copper to be produced. Okay? So with that understanding, we can now move on to the other part. We now have the complex question, which will break down. So if you are tired, I would recommend you pause the video and resume after, because this question is very important. Most of the concepts under electrolysis are going to be summarized as we answer this question. Okay, so if you have built confidence from the previous question, feel free to pause the video and try out all the questions. Of course, E is more related to the previous question. Okay, now let's start with the A. First of all, we've been told in an electrolytic device, of course, an external direct current, we understand that, is connected. Now, in this case, we are told we are using two platinum electrodes immersed in a solution, okay, of 1 molar concentration, copper sulfate, that is, at 25 degrees Celsius, which means at standard conditions. As the cell runs, copper metal is deposited onto one electrode. So that electrode, of course, we call it the cathode, and oxygen is produced at the other electrode. The two reduction reactions that occur in the cell are shown below. So these are the half reactions. Now, if you try to observe them, they are all written in the form of what? Reduction. Okay. So on the diagram above, indicate which electrode is the cathode, which is the anode, and the direction of the electron flow between the electrodes. So what do you think? So if you look at the diagram, they've given us a hint. They've told us to say this is a reaction that is happening on this electrode. Now, what kind of a reaction is this? So gaining of electrons, what do we call that? So we call that reduction. So that reduction occurs where? So this is a cathode. So that's actually where the copper solid is being deposited, even according to the equation itself. So electrons are coming from the other side, okay, which is the anode. So this is the anode. So we expect that it's at the anode where we have oxygen being produced. Okay. So we've answered the first question. Of course, just a reminder, the anode is always connected on the positive part of the battery. The negative, that's the cathode. So write the balanced net ionic equation for the overall electrolysis reaction that occurs in the cell. Okay, so we need to write the balanced net ionic equation. So one step that you can basically take to even answer that question is you need to reverse the oxidation reaction. So according to the question, we've already been given the reduction reaction, and because we've been told copper, of course, is being deposited, so it remains as it is. Now the other one is supposed to be reversed since it is the oxidation reaction. Okay, so we need to have one reaction gaining electrons, the other one losing electrons. So since we've been told on the diagram, we can see that electrons were being gained. So where were they coming from? They were coming from the other half electrode, or the other electrode of the anode. So we'd have to reverse it because that's where oxidation occurs, and oxidation is loss. Loss is indicated by the presence of electrons on the product side. So that means if we reverse it, we have water on the left in liquid state giving us oxygen gas. What else? We have 4 hydrogen ions. we have 4 electrons. Okay, and then the other equation we have is copper 2 plus. So that one is as it is. So we have copper 2 plus 2 electrons, giving us copper solid. Now you need to make sure that before you get to combine the two, the number of electrons being lost and gained should be balanced. So that means we have to multiply the second equation by 2, so it becomes 4 electrons, 2, and then we combine the left and the right hand sides. So for the left, we'll end up having water on top being combined. So water is of course in liquid state, being combined with 2 copper 2 plus in aqueous state as an ion. And then on the product side, we've got 4 hydrogen ions, we have oxygen gas, okay, and then we also have copper in solid state. So that is the balance equation for this reaction. Okay, now from there you should be able to determine, of course, the cell potential of this cell, okay, and the free energy for the reaction. So what do we expect? How do we calculate the standard cell potential? So I already told you the standard cell potential. If you don't want to confuse yourself, always just add the values. For the oxidation reaction, after I reverse a reaction, in this case we've reversed this reaction because it's oxidation, so the value of the reduction potential changes, it becomes negative. So add negative 1.23 volts plus the reduction potential of the reduction reaction. What answer do you expect to get there? So negative 1.23 plus 0.34 volts, the value is negative 0.89 volts. So a negative value shouldn't be a surprise because this is an electrolytic cell. Okay, so an electrolytic cell, we have negative value of the cell potential. And then we also need to determine the free energy for the reaction. So the Gibbs free energy, I said it's negative n Faraday's constant and then the standard cell potential. So the number of electrons that were being transferred in this case we have 4, which is denoted by n. Faraday's constant, which is 96.485, would just take it just to be the approximate value that is usually used as a constant, coulomb per mole. Those are the units. And then we need to multiply by the voltage, which is the cell potential there, which is negative 0.89 volts. Now I want you to know that volts is the same as what? Joule per coulomb, so that you can see the dimensional analysis there. So joule per coulomb there. So a coulomb will be able to cancel out, okay, and then we remain with joule per mole. So after you multiply these values, you get a positive value, 340,000 joules per mole. Now you can divide by 1,000 to make it kilojoules, which will just be like 340 kilojoules per mole. Let me even put an emphasis by showing a positive value. So a positive value, of course, the positive Gibbs free energy and the negative cell potential show that this is a non-spontaneous reaction because there is usage of DC to force a movement of electrons from the anode, which is from the positive terminal in a battery, in an electrolytic cell. What is the minimum voltage that must be applied across the electrodes to drive the reaction? What is the minimum voltage that must be supplied? So the minimum voltage, of course, is just basically going to be the same value that basically was determined for the voltage. So we need a minimum of about, so we calculated 0.89, right? So minimum of 0.89 volts is required to drive the reaction. Anything less than that won't work. Okay, so now let's create some space to be able to answer the other question, which is the last part. So just allow me to remove the questions that we've already answered. Okay. So if you're tired, again, I'll repeat, feel free to pause the video and get to continue. Okay, so this is like related to the question that we've previously answered from the previous part. So we are told again, an electric current of 1.50 amps passes through the cell for 40 minutes. So here we've got 40 minutes. Okay, so I told you to say the first thing that you'd want to do when you're trying to determine the mass, in this case, of course, asking us the same question, we need to determine the mass of that copper that was deposited on the cathode. So what do we do? So let's determine the charge. I said is current multiplied by time. Amps is the same as 1. That's coulomb per second. Remember, current is a rate of flow of charge. And then time, we also need to ensure it's in seconds so that we can just get coulomb as a result. So 40 minutes. So in a minute, you've got 60 seconds. So how about in 40 minutes? How many seconds are you going to have? So you have a product between 60 and what? So you have 40 minutes. In a minute, you have 60 seconds. Okay. So the minutes will go. And then you remain with the seconds. Now the seconds will also divide. Okay. So we'll multiply 1.5 by 40 by 60, giving us 3,600 coulomb there. So we've determined our charge, which is the first step. Now don't forget that we apply the concept of Faraday's constant. Faraday's constant is 96,500. This is the rounded off value. Okay. So I told you the units here are what? Coulomb per mole for Faraday's constant. Okay. Now we also need to take note of the cell, the half cell reaction itself. So according to the half reaction there, we've got 2 electrons of copper. We've got 2 electrons being gained by copper. Yeah, I meant to say that. Okay. So what should we expect then? So let's try to use dimensional analysis to help us come up with an answer. So we have 3,600 coulomb as our charge. I'll get the Faraday's constant. So obviously, since I want to show the cancellation of the coulomb there, since I'm saying it's 96,500 coulomb per mole, I can write it in form of the opposite so that the mole can be on top. So say 1 mole of electron over 96,500 what? Coulomb. Okay. So far we can see the cancellation of the coulombs there. What more do we need? We also need the molar mass of the copper in this case. Okay. So the molar mass of copper is grams per mole. The units for molar mass is grams per mole. So it's 63.55 grams per mole, of copper. Now according to this reaction, we are told 2 electrons are what? 2 electrons are basically gained by every mole of copper. So per every mole So we need to make sure we write it in the way that it will cancel out. So per every mole of copper, we have what? We have 2 moles of electrons being what? Being gained. Okay, let's try to see now where the units have ended at this point. So mole of copper can cancel there. Mole of electron can cancel there as well. So in summary, the things that have been used in the calculation, we are using the charge. Okay, we're using the charge, Faraday's constant, molar mass, and also the electrons. Okay, so dimension analysis will be able to guide you to come up with a basic calculation of determining the mass. So if we multiply what is on top, 3600 by 65.55 divided by 96,500, which is on the bottom, and also 2, we'll be able to get a value of 1.19 grams of copper. Okay, so that's how simple electroplating calculations are. Now, just to apply a bit of stoichiometry to answer the last question. Okay, so let's take note of a mass that has been determined. 1.19 grams of copper. So the question says, calculate the dry volume in liters measured at 25 degrees Celsius, and the pressure has been given there. So first of all, the formula, without even wasting your time, we use the ideal gas equation, because we're dealing with a gas there. Okay, so PV is equal to nRT. So if we are to find the volume will be equal to, you divide by pressure on both sides. So you have nRT of pressure, right? So take note, pressure has been given, the temperature has been given, gas constant is also always known. Okay, so 0.0821, and then we're just remaining now with N, which will be now the number of moles of the oxygen gas that we expect to be produced there. So take note that we'll just use the balance equation to help us, the balance equation that we basically came up with. So the balance equation that we came up with, which was representing the entire reaction, we had 2 water molecules reacting with 2 copper molecules. But of course I need to focus more on the product side, because that's where we have the ratio between the copper being produced. So we had copper solid plus what? Oxygen gas. So these are in the ratio of 2 to 1. So per every 2 moles of copper being produced, there is a single mole of oxygen being produced. Take note of that. That's according to the balanced equation for the entire reaction. Now, we've also determined the mass of copper to be 1.119 grams. Okay, so how do you find the mole of any given substance? So number of moles is equal to mass over molar mass. So this mass divided by the molar mass. So divide by the molar mass, which in other terms is multiplying by the reciprocal of copper. Okay, so remember the units for molar mass is grams per mole. So 1 mole per every 63.55 grams of copper. So that is just to show the cancellation of what? The units, or we are just dividing, in other terms, we are dividing the mass by the molar mass to get the number of moles. So this first calculation will give us what? The number of moles of copper. Okay. Now the number of moles of copper we are now going to use this ratio between the number of moles according to the equation that are being produced. Okay, remember this is the ratio according to the equation, the balance equation. So after determining the number of moles of copper, we're able to use that ratio to help us determine the number of moles of what? Oxygen. So if we want to find the number of moles of oxygen, then we need to make sure that the oxygen is on top. So multiply by the oxygen will go on top. Every mole of oxygen, there are 2 moles of copper solid that are produced. Okay. So at this point where the equation has reached, you are sure that we've now determined also the number of moles of what? Of oxygen that had reacted in that reaction. So after performing your calculations on your calculator, you should be able to get 0.00936 moles of what? Moles of oxygen that had reacted, or that was produced at the anode. Okay. We can now use our equation since every value is available. So our volume is equal to nRT, where n is denoting the number of moles, which we've calculated to be 0.00936 moles. The gas rate constant is 0.0821 liter atm per mole, and then per Kelvin. So the 25 degrees Celsius that we have in our formulas, we use Kelvin. So you add 273, you'll be able to get 298 kelvins. All these values are to be divided by the pressure, which has been given to be 1.16 atm. Okay, so what do we get there? So multiply what is on top and then divide by what's on the bottom. So the volume that we expect to be produced, considering an 100% efficient of the current that was used, we end up with 0.197 liters.